The main thing though is that even though we have several unknowns here, like in this case, we don't know the current in the left pipe, we don't know the current in the right pipe, and we also don't know the density of the fluid. But we can assign variables to all those. If we just list out all of our unknowns so that we can keep track of them, let's just say our unknowns are, set off to the side. We don't know the density, and we don't know the left pipe, and we don't know the right pipe current. So we've got 3 unknown values. We don't know the density of the fluid. We don't know the current flowing through the left pipe. We don't know the current flowing through the right pipe. And I think we know everything else. We know we're given all of the relevant pressure differences. We're given the strength of the pump, and we're told the current flowing in. And we know the area change for the right pipe as it spreads out. So I think we know all the other relevant values. We just have 3 unknowns. If you just have one equation relating 3 unknowns, then you can't really solve that numerically. You can't find a numerical solution. But what do you need to know in order to solve for 3 unknown variables?
3 equations?
Yeah, we have 3 unknowns, so we need a system of 3 equations. If we can establish a system of equations with 3 equations in it, that is 3 facts about how these are related, then we should be able to solve for those 3 unknowns. If the equations are nonlinear, then that can complicate things. But as long as you've got 3 linear equations, you can find a solution. If some of them are nonlinear, it may at least be possible, but there might be multiple solutions, or there might be no solution. But let's start by trying to write out the equations. We've established the unknowns. We've got variables naming each of those unknowns: density, left current, right current. The next step, I think, would be to write out as many equations as we can describing how these are related to each other. So do you know of any facts about how these 3 variables are related to each other? What do we know about? Yeah, go ahead.
We can do the current in equals the left current plus the right pipe current.
Yeah, going back to that same junction rule, let's say we apply it to this junction here, point A. The current flowing in is 13 cubic meters per second. And the current flowing out would be the left current and also the right current. So we know that the left current plus right current, that is the total current out, has to equal 13 cubic meters per second, the current flowing in. So let's start with that. We know that the current in equals current out, the fluid version of the junction rule. Left current plus right current must equal 13 cubic meters per second. So we have that solid. We know that's going to be true. That's one equation. If we can find 2 more equations linking these together, then that should be enough information. So how can we establish more equations relating these together?
What I did was I solved for, I have a Bernoulli's equation for point B to C and point D to E.
Yeah, we could write out some Bernoulli equations here. Let's say we're going from, let's say from B to C to start with. If we just write out a Bernoulli equation covering from B to C, what's changing from B to C that we need to keep track of?
So the potential energy and the pump. And
What kind of
resistance.
potential energy?
I said gravitational potential
Is there
energy.
actually a change in height from B to C?
Yeah, I thought so. Oh.
I mean, it kind of looks like it based on the diagram, but if you take a close look at the text here, it says you may ignore any changes in height between the two branches. These aren't representing different heights. I think this is meant to be a top-down view. Like you've got this, this fork-shaped pipe that's just flat on the table and you're looking down on it from above. So this is not meant to be like, C is not higher than B. C is, maybe this is like further north than B. But this is a top-down view. We should assume that this entire Y-shaped pipe is flat on a tabletop. But there are no changes in height in this entire problem. I think that's what's meant by you may ignore any changes in heights. So there's no changes in potential energy density anywhere in the system because it's all at the same height. But what else is changing from B to C? What terms would we need to include in the Bernoulli equation? Is there anything we know has to be different at B versus at C? Based on the text of the problem here?
E-pump?
Yeah, there's definitely going to be a pump term because this path is passing through a pump. So we definitely have equals work density done by the pump, which is provided. We know that's going to be 155.4 kilojoules per cubic meter. What else is happening from B to C?
There's resistance.
Yeah, there's resistance and there's fluid flowing through that resistance. So we should have a minus IR term. Is there anything else changing from B to C?
Pressure.
Yeah, it tells us there's a pressure difference. In fact, it even tells us how different they are. That pressure difference, PC minus PA, is 150.4 kilopascals. And that's from A to C, but I think we can assume that A, B, and D are all at the same pressure. They're all the same small section of pipe, so I think those are all the same pressure. So that's our Bernoulli equation from B to C. Delta pressure, which is given, equals work density of the pump, which is given, minus I times R. And we know delta pressure, that's as we're going from A to C, if you think of C minus A as final minus initial, looks like that's an increase in pressure. So positive 150.4 kilopascals. Work density of the pump, 155.4. And kilojoules per cubic meter is the same as kilopascals. And then minus I left, which we don't know, times the resistance, which is provided 1,000 kilograms per meter to the fourth seconds. So that's our Bernoulli equation that also involves how many unknowns in this case?
Only one.
Yeah, and if you've got an equation with only one unknown, you can solve that directly.
Mm-hmm.
So I think what I would do there is solve that for that left current. And once you have the left current, being very careful with the units, of course, what would you do with that?
You'd be able to solve for the right current.
Yeah, fill that in with the junction rule equation we've already established, and you can solve for the right current. And once you know both of those currents, we still need an equation relating one or the other of the currents or both of them to the density. So what other equation could we set up that will actually involve density? It looks like this one didn't yet.
You can do the Bernoulli's equation from D to E.
Yeah, if we set up a Bernoulli equation from D to E, that should work. We go from D to E. Let's see what that would look like. Bernoulli equation from D to E. And from D to E, what changes should we include in the equation?
Change in pressure and change in
Yeah, we're told the change in
energy.
pressure. It's still the same 150.4 kilopascals. Is there anything else changing from D to E? Again, we can ignore change in height because we're assuming this is a top-down view. Everything's at the same height. But it looks like the pipe is getting wider. So yeah, the kinetic energy is going to change because of that area change. So we should expect the kinetic energy density term, which is going to be density times, or density over 2 times delta speed squared. And then do we have any pump in this section of pipe?
No.
No pump, so we can leave that out. There's a pump somewhere else in the system, but it's not on this path, so we can ignore it. And we do have current flowing through a section of pipe with resistance. It's the same resistance, 1,000 kilograms per meter to the fourth per second. So we still have a negative I times R term here. And filling in what we know, we still know that the delta pressure is still going to be the same 150.4 kilopascals. That's just provided by the problem. Plus density over 2, and we don't know density, so that has to be left as an unknown. And for change in speed squared, that'll be speed at E squared, the final, minus speed at D squared, the initial, equals negative IR. And that'll be I right times the same 1,000. We still have a lot of unknowns here. We've got the unknown speed at E, the unknown speed at D, and the unknown right current, and the unknown density. So it looks like we've expanded the number of unknowns. Is there any way we can write out these speeds in more useful terms? What else is speed of the fluid related to that we do know or that we can find?
Area and current.
Yeah, we can use the established idea that current equals speed times area. We have 2 speeds here. So how would you isolate speed here? Speed equals what?
A over I.
Yeah, or other way around, because we need to divide by A to cancel this out. So current over area. And the current in this entire pipe is just that same I sub right. The speed, the area is given. We know both of the areas. That's, what was it? 0.276 square meters and 0.381 square meters. So we can find each one of these as current over area. This one and this one. Those are both just going to be I right over an area. I right over the area at E, which was 0.381 meters squared. And I right over area at D, which was 0.276 meters squared. So we can establish both of those values because do we have the current in the right pipe? Or where do we find that?
Yes, we already have.
Yeah. Because once you find the left current, you can plug that into the junction rule, solve for the right current, and plug that in everywhere you see I right, here, here, and also here. And at that point, once you filled all that in, the only unknown left will be density. And again, be very careful to actually keep track of units in all this. But that should be enough information to solve for density as the final unknown. So solve that for density once you filled in everything else. And that should tell you the density of the fluid. So ultimately, this boils down to a system of equations. As long as you've established what unknowns you're trying to find, and then maybe the unknown that the problem's actually asking for, and maybe there are some other unknowns as well that are going to be relevant. But as long as you can write out as many equations as you have unknowns, then that's a system of equations that you can, at least in principle, solve for all of those unknowns. Any questions on that so far? Yeah, definitely not going to solve this, but I do want to give you some help in terms of how to set up the equations or what equations to be looking for. Any other questions on the general idea there? All right. Anything else you want to work on? Or any other general questions? I think there was a question earlier on dealing with a circuit with multiple batteries. Let me see if I can pull up an example that would be useful there.
Yes, I was thinking about number 3 that's like on that problem set.
Okay.
Like I was like looking at it and working on it, and I am just kind of like, I just want to make sure like I know where the junction rule is supposed to apply. Yeah, so for that problem, like if we start at 26 volts and then we go to the left, when you hit point G, does like, so from 26 to point G, like I labeled that as I1. And so if we go right from point G, does that become I2? And then going towards E, does that become like an I3?
Sort of. The thing is, we only really care about current for purposes of which delta V formula. Like, what's the only delta V formula that has current in it?
Power.
Well, that's not a delta V formula. I mean, delta V for what sort of object? Like, for instance, for a battery, the delta voltage doesn't depend on current at all. For a battery, delta V is just some constant value.
Oh, like for the resistors?
Yeah, for the resistor, delta V is negative I times R, current times resistance.
Right, right.
So we only really care about current as it pertains to flowing through resistors, which means I would label current based on the resistors. Like, for instance, we know we've got resistor 1 could have some current flowing through it. So let's draw an arrow representing current through resistor 1 and label it, let's say, I1. And do we know which direction current is going to flow through I1?
Usually I would say it would go from like the positive side of the battery to the negative, but like since there's both negative ends close to that battery, does it go to the one with higher voltage?
Probably, but the thing is there's also another battery in another part of the circuit, so that may play a role as well.
Oh, so it'll go from A to B.
Maybe, I'm not sure yet, but yeah, in general, if you're not sure, you can just make a guess. Okay. The thing is, if we just make a guess, like let's say we just guess that current is flowing from left to right, and we call this current I1. And let's say we go through the whole problem, we solve for I1, If our guess turns out to be incorrect, if it turns out current is actually flowing from right to left instead, what's going to happen when we solve for current 1?
It'll just be negative, and then we can flip the sign.
Yeah, exactly. So it's entirely legitimate to just make a guess. If you already know, or if you have a pretty good idea which direction current is flowing, use that as your guess. But if you have no idea which direction current is flowing, just pick a direction and label that with an arrow and I1 or I2 or whatever. And then if your guess turns out to be wrong, then you just get a negative value for current. So that tells you, oh, current's actually flowing in the other direction. And we can do that for the whole thing. We don't really even need to worry about, well, which way is it flowing? We can just say, let's just call I2 the current in resistor 2. Let's just say this current is I2. And we can also just say, let's treat left to right as the positive direction. And we can do the same thing for the third resistor. We can just say, let's call this current I3, and let's define left to right as the positive direction. So that would be, and you can choose any direction you want to call the positive direction. Just choose a direction. In fact, you could even say, let's say I1 and I2 are to the right, I3 is to the left or something. As long as you're consistent about it throughout the entire problem. You don't want to change which direction you're calling positive partway through the problem. And then you can use that to establish loop rule equations. And once again, it looks like we have 3 unknowns. So what are we going to need to establish?
That like the total current is like in is equal to out. So like I1.
Well, for what point? What junction are we talking about here? Because we need to choose a junction to start. If we want to write a junction rule equation, we've got to have a junction to use. So what junction do you want to use here?
Could we do like I1 is equal, or like I3 is equal to I2 plus I1? Does it matter?
Which actual point on the circuit? Which one of the label points?
Could it be like G or C?
Sure. Let's take a look at, let's say, location C.
Okay.
If you take a look at location C, based on the labels we've established, what currents are going into this point?
Current 1, 2, and 3.
Yeah, current 1 is going this way. That's going into this region. Current 2 is going into this region, and current 3 is also going into this region. So current in would be I1 plus I2 plus I3. And what currents are going out of this region? Have we labeled any currents that are going out of this blue circle?
Current 2, well, current 1 is like going through it. So does it go out of it once it passes it?
Well, ignoring what's going on inside the circle, if you just look at the border, the edge, current 1 is definitely going into the circle. Current 2 is definitely going inwards towards the circle. Current 3 is going inwards towards the circle. So is anything going out of the circle?
No.
So that means current out would be 0.
Oh, okay.
If we write the sum of the current flowing in equals the sum of the current flowing out, based on the way we've set up our labeling system, all the currents count as current in. Current in would be I1 plus I2 plus I3. And none of the currents we've drawn are going out based on the directions we've chosen to draw. So current out would be 0 here. Is that possible? Is it possible for 3 numbers to add up to 0?
No, unless they're all 0.
Unless they're all 0, or unless at least one of them is what kind of number?
A negative.
Yeah. And we've already established that one or more of these could be negative. That just means currents flowing the other way.
Right.
So this is an entirely legitimate setup. It ends up seeming kind of counterintuitive because it looks like you've got all current flowing in and nowhere for it to go. But remember that at least one of these currents is actually flowing the opposite direction. It's just that in terms of the equations, that will be shown as having a negative sign in front of the current, or the current being a negative value. So for instance, just as one numerical example, this is probably not the actual answer. But let's say current 1 and current 2 are both flowing in with, let's say, 5 amps and 3 amps, and current 3 is flowing out with 8 amps. Current 3 flowing in the opposite direction means we treat it as -8. So we'd have +5 plus +3 plus -8. Those add up to 0.
Okay.
So mathematically, this checks out. Any questions on that so far? So that gives us one equation showing how these 3 variables are related. But again, we have 3 variables. So what do we need in order to be able to solve?
Like a loop rule equation.
Yeah, some loop rule equations would be good, because how many equations should we need here?
3, because there's 3 variables.
Yeah, once again, we want a system of 3 equations since we have 3 unknown variables. The junction rule can definitely be one of them. For the other 2, we'll need to draw out loop rules. So what's an example of a loop we could draw here?
So like if we start at 14 volts, so it'd be like 14 volts, and then when you go around to C and then you like go left towards the 8 volts, does that mean you're gaining 8 more volts?
Yeah. So, and the thing is, if you try writing out the mapping voltages thing we were looking at earlier, like let's say, for instance, if we call this region 0 volts.
Mm-hmm.
This battery definitely adds 14 volts. So this region will be at 14 volts. And not just that single point, but this entire zone, all these points connected by just wire, those will all be at 14 volts. And then if you go through this battery to point F, what does that do to the voltage?
It adds 8 volts.
Yeah. So from 14, we'll add 8 more, and this zone will be at 22 volts.
Okay.
The problem is we don't know, we still have 2 unknown regions. We don't know the voltage here at location A, because that's on the other side of resistor 1, and we don't know a voltage difference for resistor 1 yet. And we also don't know the voltage over here at locations G and E, because we don't know the voltage difference for resistor 2 or resistor 3 yet. We at least know A and G have to be different by how much?
By 4.
Not just by 4. If you go from A to G, what battery have you passed through?
Oh, 26.
Yeah, they've got to be different by 26. So if we label this, let's say voltage at A, V sub A, then this blue zone has to be V sub A plus 26 more. The problem is we still have this unknown. We don't know what VA is. We can label all these voltages, but we still have too much missing information. We don't know what VA is. We don't even know if it's greater than or less than 0 volts. It might be more than the voltage at B, it might be less than the voltage at B. So the mapping out the voltage approach that we've been doing in the past gets us some information about voltages, but it doesn't give us enough information to even say what the delta voltage is across any one resistor. So that's a bit of a problem. We don't know what the voltage across the resistors is yet. So this approach can be useful for conceptually understanding what's going on here in terms of, oh, there's a difference in voltage from here to here. But it doesn't really give us any more information about how the numbers are related. So instead, I think we're actually going to have to write out some loop rules. If we draw some loops, like let's say from some point to some point, like let's say we start at location A. Starting at location A, where could we go from there? We could go from A to where? What other point?
A to B. So you could just do like the big loop.
Yeah,
Or
A
like,
to B.
yeah.
Yeah, if we go all the way around the big loop, A to B to C to D to E to G back to A, the big loop. And let's say we are going in that direction, clockwise, because direction matters here. For that loop, the big outer loop, we can turn that into a loop rule equation. So as we go from A around the loop, what things are we encountering?
So you have like I1 times R1.
Yeah. Although in general, for the delta voltage for any resistor, it's not just I times R. What else do we need in the formula there?
Do we need the amount of voltage?
I mean, what is if we just go back to Ohm's law, delta V for any resistor is always what formula?
Negative IR.
Yeah, we need that negative to represent that it's a voltage drop. So if we're going through a resistor, we should write a delta V for the resistor, which is negative IR. So that's negative I1 times R1. And I think we know R1, right? That's 18 ohms. So negative I1 times 18 ohms. What's the next thing we go through after resistor 1?
The battery, so you gain 14 volts.
Yeah, plus 14 volts. Then what's the very next thing you go through?
Resistor 3 and current 3, so it'd be minus I3 times R3.
Yeah, except for one thing. We're going through resistor 3 based on the direction we chose to call positive for the current. The loop is going through resistor 3 backwards. How do you think you'd represent that in the formula?
It'd be plus I3 times R3.
Yeah. Or alternatively, you could still write it as negative IR. It's just that for current, you'd write negative I3. So you could think of this as plus negative I3 times R3. In the sense that to the right is the direction we defined as positive. If your loop is going to the left instead, you would treat that current as a negative, or current as the opposite of I3. So the formula is still negative IR. It's just that I is the opposite of I3, since we're going in the opposite direction. And the negatives end up canceling out, so it works to plus I3 R3, where R3 is, what, 9 ohms? After R3 backwards, what's the next thing you pass through?
You lose 26 volts.
Yeah, since we're going through the battery backwards, then we're losing 26 volts. So that would be plus negative 26 volts. Then we're back to where we started, so those have to add up to 0 because that's a complete loop. Why wouldn't you want to make a loop in the same direction as the current you're guessing? The problem is if we chose the loop in the opposite direction, counterclockwise, we'd be going through resistor 3 in the positive direction, but we'd be going through resistor 1 backwards. So you can't really choose a loop here that would go through both of those resistors in the direction we chose as positive. One thing you could do, when we were setting up the problem in the first place, you could say for I3, let's treat to the left as the positive direction. So that would be one way to do it. And then you wouldn't have to worry about the negative. But in general, mathematically, it works out the same way anyhow. You just choose a direction to call positive for each of the currents, and then you choose a direction for your loop, clockwise or counterclockwise. And sometimes some of the currents may end up having to be treated as a negative multiplier because your loop is going in the direction opposite from the direction you defined for the current. But mathematically, it all works out anyway. All those negatives should balance out as long as you're careful to keep track of them. Any other questions on that loop rule so far?
I have a question about like the batteries. Because like I feel like A and B, they're like between like the negative terminals of the battery. So does that mean is the voltage, there's no voltage difference would be 0 or
it just means that A and B are both at low voltages. compared to, like, for instance, point G would be at a voltage that's 26 volts higher than A, and C would be at a voltage that's 14 volts higher than B. But A and
they're
B
still
don't have to be
like
the same
current.
voltage. Yeah, because there's no reason A and B have to be at the same voltage, because they're not connected by just wire. There's a resistor in between, and that resistor can have a delta V associated with it.
Okay.
In general, the only time you would assume 2 points have to be at the same voltage is if they're connected by wire, such as C and D, for instance, have to be at the same voltage as each other. And like if we had a short circuit, like let's say we also had a path connecting A to B directly made of more wire. In that case, A and B would be at the same voltage, and we would say R1 got shorted out. But there is no such wire in this case, so A and B can be at different voltages. There's no direct path, only a path through a resistor. Any other questions on that loop rule equation so far? And is there any way we could simplify this equation? Anything we could combine or anything we can cancel out?
So the volt would just be negative 12 volts.
Yeah, the 14 volts and the negative 26 volts, those can combine. So we just get minus 12 volts. And also we've got negative 18 ohms times I1. And we've got, what happens to these two negatives here?
They become positive.
Yeah, so we just get plus 9 ohms times I3 plus negative 12 volts equals 0. And in general, what units should we expect I1 and I3 to be?
In amps.
And if you multiply amps times ohms, what would you get?
Voltage.
Yeah, that's going to be volts. So it looks like everything's going to work out to volts here anyway. We don't need to worry about any fancy unit conversions. Generally, I do recommend including units when you're working stuff out. But also, if you know what voltage everything's going to work out to, and it's all going to fit together and you don't need any further conversions, it's generally safe to leave off the units. So we can just write this numerically as negative 18 times I1 plus 9 times I3 minus 12 equals 0. Also, when you're dealing with a system of equations, it's often useful to have all the equations in the system written in the same format. Like, note that over here, we've got just something I1 plus something I2 plus something I3 equals something. I would recommend writing the other equation or equations in that same format. For instance, how would we get rid of this minus 12 here?
Add it to the other side.
Yeah, I would proceed here by adding 12 to both sides. And also, the first equation we had included I1, I2, and I3. How much I2 do we have in this equation?
0.
Right. So I find it useful just as a placeholder to also include plus 0 times I2. If one of the variables doesn't show up at all in an equation, sometimes it's useful to include plus 0 times that variable as a placeholder, just so that all the equations we're dealing with are something I1 plus something I2 plus something I3 equals something. Consistency like that often makes it much easier to solve the system of equations, or at least to keep everything organized. So it looks like that's 2 equations using these unknown variables. What else do we still need, though? How can we get one more equation that links these together?
You can make a loop with the inner, like using R2 and the battery that's 8 volts.
Yeah, if we use maybe this path And do you want to use upper loop or lower loop here?
Upper.
Okay, so using the upper loop. And let's say we also use clockwise. In that case, we're passing through some of the same stuff. We can actually reuse some of this because we're still passing through the 26-volt battery backwards and resistor 1 and the 14-volt battery forwards. So we can reuse that part of the equation. What's the only difference going to be?
You wouldn't have resistor 3.
Yeah, we're not going to have resistor 3, and instead, what are we going to have?
Resistor 2.
Resistor 2 and also
And
what
the
else?
battery.
Right, and the battery.
8 volt.
So we've still got the same I1 R1, so negative I1 times resistance 1, which is 18 ohms. We've still got the same plus 14 volts. We're still going to eventually have the same negative 26 volts. And then we're going to go through the 8-volt battery, and should that be plus 8 or minus 8 in this case?
Plus 8 because it's going, the current is going in the same direction as the battery is releasing higher voltage.
Yeah, we're going in the direction from the negative terminal, which is the low voltage side, towards the positive terminal, which is high voltage. So that is an increase in voltage. And if you're not sure, you can always label those, like just put in a little label. Let's say this is low voltage and higher voltage. So the negative terminal is always going to be the lower voltage side, and the positive terminal, the higher voltage side of that battery. So these arrows are pointing from the low voltage zone towards the high voltage zone in terms of the direction of the loop. So that is an increase in voltage as we travel along that path. Then we travel through R2 backwards. So how would we write that?
Is it like how it was before for R3? So like negative, so minus negative I2, R2?
Yeah, exactly. We're going to get that double negative again because we've got a negative IR because it's a resistor, but also we're going through it backwards relative to the direction we defined for current. So the current itself is negative I2 times R2, which was 16 ohms. And it looks like we're now back to the start. So what do these have to add up to? If we formed a complete loop, these add up to what?
0.
Yeah. Simplify that by combining like terms, canceling out the double negatives. And I would also recommend writing it in the same format. Something I1 plus something I2 plus something I3 equals something, even if you have to use 0 as a placeholder coefficient. At that point, you'll have 3 equations, 3 unknowns, all in the same standardized format. So solve that system of equations for I1, I2, and I3. If any of those are negative, that just means that current is actually flowing in the opposite direction. Any other questions on that?
Does it complicate things if you were to start, if you had I1 in the opposite direction? Like if you said that, like in your when you started at the very beginning, you had I1 is facing the right, I had it facing the left so that it made like a circuit.
In that case, it would change how we're writing the equations. Like you'd have I1 on the other side of the junction rule equation, and you'd have an extra negative next to I1 in all of the loop rule equations. But it would still work out to the same results. You just end up with I1 being the opposite number of what it was in this side. But as usual, the negative or positive sign just refers to direction of travel anyway.
Okay.
So you certainly could set it up by defining I1, I2, and I3 in whatever directions you want, even if they're not all the same direction. Just choose a direction for each one of those current arrows and be consistent about it throughout the entire problem.
Gotcha. Cool. Thank you so much.
You're welcome. And if you want more practice on circuits in general, I've got a worksheet of practice circuits. If you go to math.andcheese.org/P7B, there's a circuits practice worksheet. It doesn't have any instructions written on it. It's just a bunch of circuit diagrams. But for each one of them, all of the batteries and resistors are labeled. Your challenge there is find all of the currents. And you can use a similar setup to this, either by writing out loop rule equations and junction rule equations and solving the system of equations, or by mapping out the voltages everywhere in the circuit and simplifying resistors. So give that a try, and I will see you next time.
Thank you.
You're welcome.